So let's start. Welcome to our machine learning lecture. I would like to start with some recap of what we did. So last time we started by raising some regression problem where we had some very complex distribution of samples, and in the original space fitting a linear model to this complex observations is problematic. So this is the classical model of y is equal to k times x plus d for the one-dimensional case. And we found out, well, a reasonable strategy to improve the quality of our models is actually to predict the same, but in a feature space where we had phi of x, and we transformed these individual points by some feature transformation phi of x. And then ideally, a linear model could explain these points. And we said, okay, we define this model to be y is equal to a times w. Remember, underline denote the vectors. We omitted today for sure. We have too many equations to write down. So we keep it simple. Everything is a vector or a matrix. Greek symbols can be scalars. Come to that. Now, this is very nice. So this feature transformation helped us to derive a very intuitive solution. So we said this W can be computed as A transpose A to the power of -1 times A transpose times Y. That was our derived solution, where we defined first an objective, computed the derivative with respect to our W parameters, set it to 0, and we solved it for W, and that was the result. And we figured out that this result might be problematic when A is not full rank. For that, we said, okay, let's introduce some regularization term. In this time, today we call it gamma prime, because I will introduce another gamma today. So let's call it gamma prime. It's a hyperparameter that we can set, and we set it to very small numbers, and that helps to regularize our inverse. Now, this is great, but what would be better is not to predict a single value here along this line of our model. It would be nice to also predict the uncertainty. Let's say for this region here, we have a relatively small uncertainty, and here where you see the model fit is a bit poorer, might have a very large uncertainty. That would help you to interpret the predictions. So today, we will follow a different idea. The idea is that we define a model here that is probabilistic. So we define a distribution over our prediction y, P of y. And typically for Gaussians, we will need to express that in terms of mean and the standard deviation. I'm not sure if this is the best color I could use, but I use it for the moment. So we turn our deterministic model into a probabilistic model where we have P of y, given some AW and some uncertainty. And the same for our W parameters. We will also turn that into a distribution where we compute these model parameters P of W, given our data samples represented by the matrix A and Y. And this is the big question, how to compute that. And that's what we want to do next. So the game is clear. We will perform a transition. We performed the transition from the original linear regression into a feature transformed linear regression, and now we will apply a probabilistic approach to that in the feature space. So A is still a feature transformation of our input samples. Oh. We don't need that. It's good. Okay. Let's recap one more thing. The Bayes rule. Remember last time we defined joint distribution P of A and B is given as the conditional P of A given B times the prior P of B. And due to the law of exchangeability, we could replace that by P of B given A times the prior of P of A. And with that, we rearranged these terms and said, okay, for P of B given A, we can define now the Bayes rule where we have P of A given B times P of B divided by P of A. You remember that. The important point was, well, this was the posterior. This is what we want to know. This term here, the conditional, is our likelihood. That's actually what we measure, what we observe, what we can compute. Observations, measurements, and so on. The last term, actually the last two terms, one of them is the prior. The prior helps us to integrate existing knowledge that we have already. We will use this prior today. And then there's the final last term. This is the normalization term, which could be expressed using the marginal. So we compute the integral over the product of the likelihood times the prior, or we leave it as it is. Now, we will use this Bayes rule, plug in our problem statement that we phrased here on top, where our goal is to compute the W parameter. Actually, we want to compute the distribution over our model parameters W. So this is our posterior. Let's put it on top. So from the Bayes rule that we derived just P of A given B times P of B divided by P of A, we say we want to learn W. So we want to compute the distribution over W given our transformed input data samples and our targets. Now this is given by the likelihood, how likely we can explain y, our model predictions, using our feature transformed input samples, our model parameters w, times the prior p of w, divided by p of a, which is p of y given a in our case. Now, we will use Gaussian distributions for that, and we will derive the maximum a posteriori solution. A posteriori because of the posterior that we want to compute here. So we will say we will neglect the normalization term. I mentioned that already once. If you want to compute the maximum parameters, the parameters that maximize your likelihood times prior, then we don't need the normalization term. So we say this is proportional to P of y given A at W times P of W. And the next step is that we will actually use a definition for these two distributions. We say this is a Gaussian distribution. Check that I don't make a mistake here. Where we use our model, y is given by A times W, with our data uncertainty, times the prior that is also a Gaussian distribution. And for simplicity, only for simplicity, I will assume here a zero mean scalar variance Gaussian prior. So this is 0. And here we have now, I'm using now this lambda as mentioned in a particular form. Lambda is now defined as precision. So that's how we denote that. It's actually the inverse of the standard deviation that is now used here. It only has mathematical reasons why I do that. It simplifies later on our derivation. So this is our model assumption that we can model these components with Gaussians, and the result is also a Gaussian. I'll put it now here. That's actually confusing if I put it here. This P of W given A and Y is also a Gaussian distribution over W. And now we need two model parameters, two, not only a single one. We have a mean value, and we denote it by, and put that right, that's exactly like in the lecture script. W given our targets, and typically we have also some covariance matrix of sigma of W given Y. This W given Y expresses these dependencies that we have. So our goal is now to compute these two values. That's the model learning part. So instead of using this least square regression result, or the regularized least square regression result, we will compute these two values. So now I need to clean one or two blackboards anyways. I will clean that one now. So the distribution P of W given our model matrix A and our targets Y is proportional to the likelihood P of Y given A and W times the prior. Now we are interested in the optimal parameters W. Now we define this as maximization problem using the argmax operator over all possible W's. Over the log likelihood. So we define here the log of already our likelihood times the prior times P of W is our prior. To be correct, you would need another set of parentheses here for the argmax operator. I will omit that in the future. Now, what is the log of the product of these two distributions? Speak out loud. So it's the log of the likelihood plus the log of the prior. This is nice. So now plugging in our Gaussian distribution assumption, this is the assumption that we make. Our modeling assumption is that all distributions are Gaussians. So we have the log of our likelihood, that is A times W, given sigma squared as standard deviation, plus the log of our prior, which is a zero mean gamma precision prior. And here this is actually also needs an identity matrix because W is a vector. But this is a scalar. So Greek letters are scalars, all other letters are vectors. Now, to see why we apply the log, this is a side equation which is not so important. The log of a Gaussian, x given mu and some sigma covariance. It's nothing else than the log of 1 divided by C1. C1 is now, remember, this 2 times pi times the square root of the determinant with the power of d dimension. So this is a constant for us. We don't care. Yeah. Times the exponential. And now in our case, we don't have a full covariance. We make it simpler, our life. We have a scalar covariance here. Make it easier, because then I divide here 1 divided by 2 sigma to the power of 2 instead of having the full covariance. And now remember, we had these vectors x and mu, and we computed here the square difference. Now, if you apply the log to this term, what happens? This product becomes a plus, so you can separate it. You can compute the log of 1 divided by C1 and the log of the exponential of this term. So this is then minus C1 minus 1 divided by 2 sigma to the power of 2 x minus mu transpose x minus mu. And that's the reason why we applied here the log trick. We are interested in the best set of parameters, W star. So computing the argmax over all W's. And we can transform our posterior using the log function. We don't care. We are anyways just interested in the best W values. We're not interested in the exact value. We drop the normalization term. We can apply the log transformation. And if we apply it, we remove completely this exponential term here. Therefore, this is called the log trick, where we computed the log likelihood. And now what remains is this constant C1, which we are not interested in our optimization, because we will compute an objective, compute the derivative of this objective with respect to W. W is not part of C1. It will cancel out. So let's apply this simple trick here to our equation. This way. So W star is given by argmax for W of, don't make a mistake here, log of our likelihood plus the log of our prior. So this is the arc max over W of, then we had minus C1 minus 1 divided by 2 sigma squared. Then we had A times W. No, it's Y minus A times W. To be precise here. Transpose Y minus AW. This is the first part. And now the second part. Minus C2 minus 1 divided by 2, the inverse of lambda. So it could be on top already of this fractal. And as the mean is 0, A times W is 0, we have only W transpose times W. This is the last term. Now, let's get rid of all these minus signs. We turn this into an arc minimization problem. We already remove our constants. We don't need them. So we have plus 1 divided by 2 sigma square. Then already apply the transpose operator here. You remember that trick here? Do exactly the same. Then we have plus lambda half W transpose W. So what's next? Minimization problem as last week. So what is the natural next step that we will perform? So we solve this product here. I could define an objective, but I anyways need another blackboard. I will simply write it down now for us. And then we start on a fresh blackboard. So we have y transpose y, then we have minus w transpose a transpose y, minus y transpose a w, plus the quadratic term w transpose a w, and this prior term. Parenthesis is missing here. Now it looks correct. Put that on top such that you can read it like that. And I start with that blackboard here. So W star is given by the argmin of W of some objective J. Now I define this J again from the top. So we had 1 divided by 2 sigma square. And so let's write out W transpose W minus 2 times what was it? Y transpose A W, Y transpose A W plus W transpose A W plus lambda divided by 2 W transpose W. This is J. Don't need the parentheses anymore. All signs are correct. Yeah, perfect. So next step, we compute the derivative with respect to W of J. And this is simply given by the scalar times the derivative of this term here. So this part cancels out. Here we only have minus 2 Y transpose A. Here we have plus 2 W transpose A plus the scalar. And here we have a quadratic term, so we have 2 times W transpose. So this cancels also out. Now we set it to 0 and we solve it for W. That's it. So this is minus. So we put it on the right-hand side. So what remains is 1 divided by sigma squared W transpose A plus lambda times W transpose is equal to 1 divided by sigma squared Y transpose A. Because we said this is 0. Now I'm doing 2 things. I'm multiplying everything by the scalar, sigma squared, and I apply the transpose operator because we are interested in W, not W transpose. So here I have to be careful. This sigma squared cancelled out. So we have A transpose A times W plus sigma squared lambda times W is equal to A transpose times Y. And now I can solve it finally for W. You see, I have the W here. So this term here in the end, I hope you can read that, can be simplified by A transpose times A plus sigma squared lambda times the identity matrix times W. So this is the same. And if I compute now the inverse of that and multiply both equations from the left-hand side with it, then I get the result. This is the result of the MAP solution, which looks very similar to what we derived last week, if you look at it. What is the difference compared to regularized least squares regression? Any idea? Look at the equation. Oh, we don't have it anymore. Deleted it already. So this is the pseudo-inverse, the regularized pseudo-inverse. Sigma squared was part of our likelihood distribution that models the data noise of our model. The new term that we have now is from the prior. The prior uncertainty using this Gaussian distribution with the zero mean lambda precision. Now this term models our belief in the prior. So I put that on top now. And I take this one. So let's wrap up what we did. Yes, yes, sure. Like that, huh? Oops. So I think I also summed up everything. Ah, yeah, yeah. A short summary, in between summary, because we still have time. So we started out with a deterministic model where our predictions are simply given by our feature transformed input data times W. We turned that into a probabilistic model where P of W given A and Y was per definition a Gaussian. This is the wrong symbol. Definition. Gaussian, where we had this mu W given by and some covariance W given by. We solved that using Bayes. The argmax of the log likelihood. Turned the argmax into an argmin problem over W. We computed the derivative with respect to our objective with respect to our parameters, set it to 0, and solved it for W star. I can write it down here. In the end, our W star was very similar to the regularized least square result. The only difference is that we have this additional regularization term from the prior. Now this W star represents our mean. Green. Green is nice. These are our model parameters that we learn from the data set during training. So this was the mean. What about the covariance? So for deriving the covariance, you need to apply full Bayesian inference. It's depicted in the script. I will write down the solution. And we discuss the solution. So the covariance is given using our prior definition, one has to say. by lambda times the identity matrix plus our data uncertainty that is transformed using A transpose times A to the power of -1. So you have to believe me that for our choice of prior, this is the solution. You can derive it yourself by looking at the script. Yeah, good point. Plus, thank you. We always had a plus because we add some regularization term. All right. So you see that solution here on page 19. So one last thing. Let's put the whole thing into a big picture. We are talking about machine learning approaches where we learn a model first from a training data set, and then we want to evaluate it on a test data set. We want to make predictions with it. Let's discuss that. So the general process is that first we have the model learning phase. So given X and Y, we computed our mean and our covariance. These two things define our prior P of W So this is the learned model. Model learning is done. We use the data, done. Part two is testing the model on new, unseen data. Typically denoted by Y star and some X star. X could be a matrix, Y could be vector. Let's keep it simple. But we have new data. So how do we do that? See if that is readable. Yes, looks good. So let's start out with the joint distribution of the new data and our model parameter set W. Now the joint is given by the conditional P of Y star given W times our prior P of W, which is nice. We have the prior from the model learning part. So we want to make use of that prior. But we are not interested in the joint. We are interested in the single prediction. So P of Y star. What can we do to compute this one? if you look at the join and that the distribution of P of y star. This is the marginal of the joint. P of y star dy. Now, if we plug in our product, we have the likelihood times the prior dy. Now, this P of y star can be computed in closed form if we use Gaussians. Luckily, we can do that because this is our likelihood. So this is y star given a star times w. A star is now computed from x star. From this, we compute our feature transformed matrix A star. You see the difference? Testing, training. Times our prior, Gaussian prior over W. Now green, where was green? Green is here. Our two model parameters, mu of W given by, and our covariance, sigma of W given by. D by. Now this can be computed in closed form using Gaussian identities. So this is something you would need to look up, some cheat sheets. I will simply write it down. In the script, you find the solution, and we discuss it again. So we compute the distribution for predicting y star, which is given by A star times our mean, green, mu of W given by. So actually we transform our prior mean using A star, which makes sense because if you think of our model was A times W. Now we have A star for the new unseen data. We don't have A anymore. We only have W. And W is given by the mean and the covariance. So it's A star times mu of W given by. And then we have the feature transformed covariance of the prior. Again, green. So it's A star times sigma W given by times A star, but transposed. Otherwise, the dimensions won't match. So for a new unseen data point, we generate a mean. This is the mean prediction. And some uncertainty estimate. As promised in the beginning, remember, we said we would like to have not only a single prediction, but also like to have the standard deviation. Now we get it. Using Bayesian feature regression. The thing is, the prior mean is transformed using A star, and here the prior covariance is transformed using also A star. Any questions? This was the result of the model learning part and of the evaluation of the test itself. P of y star is given by the Gaussian y star, given a star, the prior mean, and the transformed covariance of the prior. Transpose. This is the result of the test phase.